I'll be doing problem number 61. An enemy ship is on the east side of a mountainous island, as shown in the figure. The enemy ship has maneuvered to within 2,500 meters of the 1,800 high mountain peak and can shoot projectiles with an initial speed of 250 meters per second. If the western shoreline is horizontally 300 meters from the peak, what are the distances from the western shore at which a ship can be saved from the bombardment of the enemy ship? So here's the diagram that the textbook has. And so the black and blue lines represent the trajectories of the different angles at which the enemy ship can shoot the projectile. So as you can see, the blue line is the trajectory at a lower angle that will produce the greatest projectile distance in the x direction, and the black line represents the higher angle at which the enemy ship will shoot it, and it would just barely pass the peak. And so this was you don't want to be in between here, because this is where you can get hit by the enemy ship. So the question is asking, how far away from the shoreline can you be from here to here? What is this distance, because this is a safe distance? Or how far away from here do you have to be from the shore, because you'll be safe here and here. So you'll be finding this distance and then that distance. All right, let's start by drawing a diagram. So to represent the enemy ship, I'm just gonna draw this line here. This theta is what we're trying to find. I'm just gonna leave these as variables for now. So that's the x component of the enemy ship projectile and the y component of the enemy ship's projectile. Here's the mountain peak. The peak is 1,800 meters tall. And so the lowest trajectory, which will produce the greatest x distance, is this. And just now in the figure, you could see that for the longest trajectory, exactly right in the middle here, at the highest point of the projectile, happens to be the peak of the mountain as well. And so the second trajectory, my drawing's a little bit off, but it's the higher angle, but it comes down, and the highest point of the projectile is actually kind of off, is not in line with the peak. And so the shore is 300 meters. I should have drawn this better, but this little distance is a safe zone. And so is anywhere past this point is also a safe zone. Anywhere here, you will be hit. Okay, so I forgot to write that the enemy ship is 2,500 meters away from the mountain. So I want to start off this problem by setting up a kinematic for the projectile of the enemy ship in its long trajectory, because I know for a fact that right in the middle of its longest trajectory is also happens to be the peak of the mountain, right in the middle there. So I know for a fact that if I set it up from here to here, that the displacement in the y direction will be 1,800 meters, and that my displacement in the x direction is 2,500 meters. So I'm going to set this up as the far trajectory from the start to the peak of the mountain. We'll do the we'll set up write our givens for the x direction first. So in the x direction, initial velocity and final velocity will just be v initial cosine theta. Acceleration will be 0, and time you don't know, and you know that delta x in the x direction to the peak of the mountain is 2,500 meters. In the y direction, your initial velocity will be vi sine theta, and you don't know your final velocity, or more like it's actually 0 there, sorry. A is g, acceleration is g. You don't know time, and your displacement is 1,800 meters. Okay, so you have two unknowns. You don't know theta, and you don't know time. So I want to use the kinematic equation that has these two unknowns and utilizes these two pieces of information because we have them. And that equation is this one. Delta x equals initial velocity times time plus 1/2 at squared. So I'm going to set up this equation in the y direction first. And so I'm going to call the y displacement just y, and so initial velocity is vi sine theta times time plus 1/2 g t squared. Now I'm also going to set up this equation in the x direction, so I'll call the x displacement just x. That will equal its initial velocity, which is vi cosine theta times time, and the rest will cancel out because acceleration is 0. And so just looking at these two, I can actually isolate t here and substitute back that expression to here, and so then I can start working with it from there. So if I isolate time for the x direction kinematic equation, I'll have t equals x divided by v initial cosine theta. And so once you have this, you can plug it back, substitute the t back into this y equation, and we can start working from there. So I'm going to start substituting in. So y equals vi sine theta times time, which is this entire expression, x divided by vi cosine theta, minus 1/2 g times time, which is again this entire thing, x divided by vi cosine theta, then squared. Now I'm going to multiply. So I have x v initial sine theta divided by v initial cosine theta minus 1/2 g, and then I'm going to, distribute the squared, so you get x squared, and then v initial squared, and then, or instead of doing that, I'm just going to write it like this for now. V initial cosine theta squared, and distribute the squared. Now, you can see that v initial will cancel out here, and that this half g, you can actually visualize this g over 2. And so I'm going to clean this up a bit. And oh yeah, once you cancel that, you can see that sine theta divided by cosine theta is actually tangent theta. So you're going to rewrite that as x tangent theta minus, and since this is technically, g over 2, you're going to multiply these two, so you end up getting gx squared, and then 2 times this entire thing. So let's do that. You will have gx squared divided by 2. Now I'm going to distribute the squared again. V initial squared and cosine squared theta. Once you have this, you're trying to solve for theta. So what you want to do is combine tangent theta and cosine squared theta somehow. So what you can do is do y equals x tangent theta, but you can actually rewrite cosine squared theta as secant squared theta on top. So you're going to do that. Once you have secant squared theta on top, using trig identities, you know that secant squared theta is actually tangent squared theta plus 1, which gets us one step closer to combining tangent and secant. So let's do that. The trig identity is this, by the way. Divide everything by cosine squared theta. You get tangent squared theta plus 1 equals secant squared theta. So I can plug this in place of secant, and then I can start combining tangent. So let me do that. X tangent theta minus gx squared tangent squared theta plus 1, all divided by 2v initial squared. So now once you're here, you want to distribute gx squared to tangent squared theta and 1. So let's do that. Y equals x tangent theta minus gx squared tangent squared theta plus just gx squared, all divided by 2v initial squared. Okay, so now you can see that this is starting to look like a quadratic. The term that we're solving for is tangent theta, and so you have tangent squared theta and tangent theta. So let's rewrite this in a way that is more quadratic equation friendly. So I'm going to do y equals x tangent theta, except this time I can split up this fraction. So I'm going to rewrite it as minus gx squared tangent squared theta divided by 2vi squared, and then plus gx squared divided by 2v initial squared. And so this is minus the entire fraction, so let's keep that in mind. And so just so we don't complicate things, let me distribute that negative real quick. So then it's minus gx squared tangent squared theta over 2vi squared minus gx squared over 2vi squared. So now that our signs are correct, let's put the tangent squared theta in front, the tangent theta in the middle, and that at the end. And then plus x tangent theta minus gx squared over 2v initial squared. Now I'm going to subtract y so I can get 0 here, and I'm going to subtract y and also divide everything by -1 so I don't have this negative term in front, so it's a little bit easier to solve. Then I'm going to do gx squared tangent squared theta. And what I'm also going to do is move the tangent squared theta term out here so it's easier to visualize. Minus x tangent theta plus gx squared over 2vi squared. And so instead of minus y, it's now plus y. And so the quadratic, this is your a term, this is your b term, and this entire thing is your c term. Okay, we can finally start plugging numbers in. Just to remind you, x is 2,500 meters, y is 1,800 meters, and our initial velocity was 250 meters per second. And so let's start plugging everything in. We have 0 equals 9.8 times x, which is 2,500. I'm going to leave units out to make it simpler. Divided by 2v initial. Don't forget the squared. Tangent squared theta minus 2,500 tangent theta plus 9.8 times 2,500 squared divided by 2 times 250 squared plus 1,800. So plug everything into your calculator, and you'll find that this thing gives you 490 tangent squared theta minus 2,500 tangent theta. And all this, when you add it together, you get plus 2,290. So plug that into our quadratic equation solver. I already have it out here. 490 x squared minus 2,500x plus 290. Plug that in, and you'll get 1.197. So you'll get tangent theta equals 1.197. And if you do it again, you get your other value, which will be 3.905. And so in this case, both of these values are important. One of them is not extraneous. So you'll find that, let's set tangent theta equal to each of these so we can get both the angle, so we can get both angles that the enemy ship fires the projectile of. So tangent theta equals 1.197. That will give you tangent, or theta equals 50.12 degrees. Do it again for the other one. Do arc tangent, and you get 75.64 degrees. And so going back to our diagram, where these two angles is, the longer trajectory, that will be 50.12 degrees. And for the higher trajectory, that will be 75.64 degrees. All right, now that you finally know these two angles, your job is to find out the total displacement in the x direction for these two angles. And so from here on out, it's like a simple kinematics problem where you're given theta and initial velocity, and you just gotta find delta x. And so now you know theta. We're gonna do 50.12 degrees first, and initial, and you gotta find this displacement. So let's set up our givens again. In the x direction, we have v initial cosine theta. V final is the same. Acceleration is still 0, and time you don't know, and delta x you don't know. In the y direction, your initial velocity is vi sine theta. Your final velocity, since now we're not calculating it from here to there, we're doing it from the start all the way to the end. So it's going to be the same, but negative vi sine theta, because it's returning to the same level. A is g, and you don't know these two. So let's solve for, let's write out the equation for displacement in the x direction first, and we'll go from there. And of course, everything else, all this will die because there's no acceleration. And now let's come up with an expression for time in the y direction. So we'll do vf equals vi plus at. Time is negative vi sine theta minus vi sine theta divided by g. And so time, we can combine those two into negative 2 vi sine theta over, since g is a negative value, we do negative g. And so now it's positive. Don't have to worry about that anymore. So once you have that, you're gonna plug this expression back into time for displacement in the x direction. So let's do that. Delta x equals vi cosine theta times time, which is 2 vi sine theta divided by g. And so once you have this, you can combine it into, is it 2 vi sine theta multiplied by vi cosine theta, all divided by g. Plug all your numbers in, and you'll get the total displacement in the x direction for the longest trajectory will be 6,275.97 meters. And so you actually want to minus 2,800 meters, because what you just solved for the longest trajectory, which is the blue line, we solved that now. This is 6,200 meters. You want to minus 2,800 meters, 2,800, because it's 2,500 plus the 300 shoreline. And then the question asks that this amount of distance, that's how far away, and from here on out you'll be safe. They want to find out what that distance is. So that's why you minus 2,800. And so you'll get 3,475.97 meters. And let's do the same, but for 75.64 meters. And we can just straight up plug into here because we already solved for that expression. And so you lose sine of 75.64. I'm just using this again. Vi cosine 75.64 divided by 9.8. Once you plug this into your calculator, substituting 254 Vi, you will get 3,064.6 meters. And again, you have to minus, or you have to subtract 2,800. Now delta x equals 264 meters. Okay, so what do these two answers mean? Returning to our diagram, 264 meters is this distance, while the other answer, which is 3,475.97, that's the distance away from the shore, from there to there. And so that's problem number 61. Here's all the work, in case you need it.